continuous. So it's said to be continuous if basically, the way I think about it, like if I put a pencil on there and I never have to pick it up. So if I have to put a pencil on a graph and I never have to pick up the pencil forever, all the way from negative infinity, or wherever it starts to wherever it ends, if I never have to pick up my pencil, it is continuous. So that means there are no breaks and there are no holes. No breaks or no holes. But once again, I'm just like, can I put my pencil on it and keep it there forever? Or do I have to pick it up at some point and restart somewhere else? If there are breaks or holes in a graph, well, obviously it's not continuous, so we put discontinuous. I usually just say it's not continuous. A lot of math books have this discontinuous, so I'll write that down. And I don't know why, it might be just a disconnect of when I learned it and how my verbiage works, but I usually didn't say discontinuous, I just said it's not continuous. I don't care which one you use. Just realize if I ask, is it continuous, you should be able to say yes or no. That's your big thing. Right now, can you say it's continuous or not? Well, if it's discontinuous or it's not continuous, it falls into one of three big branches. One, you have some sort of asymptote. Two, my graph jumps somewhere else. Or three, there is a hole in the graph where I have all this stuff, skip that one little point, and then we go on. If we have a vertical asymptote, notice we're going from like negative infinity to positive infinity. There's no like clear place where I have to put my pencil down. That's called infinite. It's called infinite. It's an infinite discontinuity. Once again, you don't know where to pick up your pencil, you don't know where to put it. However, here, if I told you where do you pick up your pencil and put it down, you're just like, oh, I pick it up here, and I put it back down here. So it's not infinite because I'm not going to either infinity. Now, think about what we do here. We have to jump from one graph to the next. And that's what it's actually called. It's called a jump. I've also heard it called a skip continuity. We're going to use the term jump, but if you use skip, I'm not going to take any points off because you're jumping from one graph to the next. I am jumping from here to here. Oh, hop, sure. Well, never heard it called the hop. And then our last one. That one is, I have an entire graph, but I want to remove one point. So I have a graph. If I graphed this on my calculator, you wouldn't see this hole. You have to tell someone, hey, remove this point. That is what it's called. It's called a removable discontinuity. So it's removable. Did I miss anything else? No. Removable. So those are the three types we have to do. So when we get to like your homework or you need to explain something to it, someone's going to ask, is this continuous? You go yes or no. If it's not continuous, then you have to pick from one of these three. And if we look, that's the very first thing we need to do. We need to determine if the function shown in the on the graph is continuous. If not, identify the type and location of the discontinuity. Now, here's the thing. If I ask for the location of a discontinuity, I don't want a point because it doesn't make much sense for me to give you, I don't know, a point here. I want to know at what x value do I need to skip. So these are x values. So when I ask you to name the discontinuity or the location of it, I'm asking what is the x value where this happens. So think about this. The only time we have to put a point right now is if I ask for intercepts. If I want zeros, I want x equals something. If I ask for increasing, decreasing, or constant, you give me the x values from negative infinity to 2. If I ask for the location of a discontinuity, you give me an x value. So most of the time you're giving some sort of x values. That's our big thing. Domain, x values. The only thing we don't are intercepts, I need a point, and range, I need y values. But everything else is I'm basically asking for x values. So if you're not sure what to do, give me x values because more often than not, you'll be correct. If you're just caught between, do I need a point or an x value? Maybe choose x value because you're more likely correct. All right, First thing, is this one continuous? If I put my pencil on, even if I start here, I have to pick it up, put it back down, and I have to go. So it's not continuous. It is discontinuous. Discontinuous? No, that's not a word. It's not, it's discontinuous. I can say words sometimes. All right, so since we know it's not continuous, we should put what type it is. What type is this? Is this jump? Is this, I shouldn't have led with the correct one. It is a jump. It is a jump discontinuity. Let's just put a jump disk. I'd be okay if you just said jump. As long as you can explain to me it's not continuous and it's a jump. I'm good with that. All right, then I need a location. I don't want you to give me this point. That's wrong. It's just the x value. I just need the x value. So when I ask for where is it, you're going to go, well, that's where x equals 1, 2, 3, 4, 5, negative 5. So it happens where x equals a negative 5. And the reason why we have to give an x value is when it's an infinite one, there's definitely no place to put a point. So we use all of the discontinuity. We always just use the x values. All right, our next one. If I put my pencil at the very bottom of this graph, and I go up, at any point do I have to lift up that pencil? No. What does that mean?
Infinite.
It's continuous. It's infinite. It is continuous. Now, it doesn't have to be infinite to be continuous. Let me play a little devil's advocate real quick. Let's say I had this graph here. So picture this with me. That's my entire graph. When I put my pencil down, do I ever have to pick it up to finish the graph? No, which makes it continuous. This would be continuous because I never had to pick up my pencil. Now, if I had more, like I skipped up here, then it'd become like a jump. But if you can draw the entire thing without lifting your pencil, it's continuous. I don't want us to think, oh, it's got to be infinite to be continuous. It does not. So on this one, that makes it easy because I just have to put continuous. Our next one, is that continuous?
No. Wait, how's that one continuous?
How is this one continuous?
Yeah, I thought it would be infinite.
That's not an option.
Oh.
The only option we have is either it's continuous or not continuous. And if it's not continuous, I have to name which one of those three. There is no infinite. Is it continuous or not? It is continuous because there's no breaks or anything in it. So it makes it continuous. Now, this one, yeah.
Type of location, you just put...
There is no location. There's no discontinuity. So it says, if not, identify the type and the location of discontinuity. Since we don't have a discontinuity, we just go, oh, continuous, and I'm done. Because it meets the first thing says, determine if the function shown is continuous. It is continuous. Then we go on to if not. Oop, I don't have to read any more because it already is continuous.
Okay.
We don't have to put it's continuous over the whole thing. That's what it means to be continuous. Continuous automatically means it's continuous everywhere. Okay? All right, our next one. If I had my pencil on here, could I draw this entire thing without picking up my pencil? Yeah. No. Because, picture, even if I had a pencil that went up to infinity, I would need to pick up that pencil and go back down to negative infinity to draw this bottom one. So there's definitely a place where I have to pick up my pencil and do this bottom graph. I kind of have two graphs. That's why I kind of look at continuities. How many graphs can I see need to be drawn? So this is definitely not continuous. What kind of discontinuity would it be? That would be an infinite discontinuity because I can't do this entire top graph and bottom graph without lifting up my pencil. So this would be an infinite discontinuity. So I'll put infinite disc. And where does it happen? Well, it happens at the asymptote. So you just need to figure out where that vertical asymptote occurs at. That's at x equals 1. So at x equals 1, if you input 1, you have a problem. That's where you switch from one graph to the other graph at x equals 1. Once again, if I had a magic pencil that could go all the way up to infinity, at 1, I have to go all the way back down to negative infinity to finish off this graph. Does that make sense? Okay, then do those next three. Do those next three. While you work on those next three, I'm also going to quickly check homeworks. We had 2 homeworks due today. We had 2.1 and 2.2. All right, let's reconvene. Number 4, is that continuous or discontinuous? It is continuous. If I had a magic pencil that could start all the way at negative infinity, I would never have to. And in fact, the only time you have to worry about is the place you're zoomed into. If I could draw what I'm zoomed into without lifting my pencil, it is continuous. Remember, your answer is just continuous. Do not put anything else. If you put like x equals 3, that also means that it's not continuous. So make sure if you put continuous, you are done. Yes?
Can you just check this really quick?
Oh, we're going over them.
Oh, okay.
Yeah, we're literally going over them.
Bro, get a better fade.
All right, number 5. Number 5, is it continuous? No, it's not continuous. So that means we need to decide, is it jump, infinite, or removable? It is removable because it's just a straight line with one part missing. If you see just that hole, that is a removable. Removable disk, which means I need to give an x value. You should have said x equals a negative 3 to get that 100% correct. Am I correct with that? Okay. All right, is the next one continuous? No. How many discontinuities are on this graph? There are 2. Let's handle the first one. Let's handle the vertical asymptote. What does it mean it's a vertical asymptote? Is that a jump? Is that infinite? Or is that a... So it's infinite. So we have an infinite discontinuity at x equals, looks like 2. What's the other one? Removable. Rem disk. And that's at x equals 1, 2, 3, 4. X equals 4. Go.
Could you do the x equals and then the bracket thing for this one?
I see what you mean. I just want to make sure before I...
The lower number in front of the higher number.
Yeah. So the question is, can I just give my x values? So rather than writing this, can we write this? Hey guys, pay attention to this because this is important. I don't really want to see this. And the reason why I don't want to see this is because I want to know what discontinuity is happening at those individual things. So if you just tell me it's got an infinite discontinuity, a removable discontinuity, and it's 2 and 4, my next question would be, well, which one's removable and which one is our infinite one? That's why I would prefer that you have something like this, or at least an arrow pointing to it. So Lalo, if you decide to have it in that one, just have an arrow that points to what one goes with what, and then I'm cool with it. But just think about my next question. My next question is going to be, which one goes with what? If you don't have that answered, you're technically not fully answering the question. Is that clear on why I need that clarification? Okay. Yeah.
But if it's the same, do we have to mark them as different ones? Like if it happens twice.
Oh, if they're both removable discontinuities? So if like I have 2 that are missing and it's the same one, then you could just list them in order. So if I have like 3 removable discontinuities, so if I go here and I removed a bunch of points out of it, so if we looked at that one graph and I decide to say, well, remove there, if it's all the same discontinuity, then you could do your x equals brace and all the numbers. Because my next question would be which one's which, but they're all removable discontinuities. So you'd be like, Mr. Pabian, why are you asking me if you already know they're all the same? All right. Good? All right. The last thing we need to talk about is end behavior. So we're almost done. We just need to talk about end behavior. Now, here's the thing about end behavior. You need to know what you're discussing with end behavior. I.e., if I look at end behavior, I have to say, well, what happens when I go left really far? What happens when I go right really far? But we don't write it like that. In math, we don't say go left really far and find the point or how far you go. So think about what we're about to do in terms of left and right. Think about that. I'm just trying to describe go left and go right really far. That's what end behavior means. End behavior means I don't care what happens in the middle. I just care what those 2 arrows are doing when they get really, really big and really, really small. So we're just thinking left and right when I describe this. All right, instead of saying left and right, we use x values. So if we read this, As x moves towards positive infinity, which direction are we going if x gets really, really big?
Right.
We're going right. So basically this is saying, what happens when I go right? And negative infinity. If x gets really, really small, which direction are we going? We're going left. So this is saying, what happens when x gets really big? We're going right. Or really small, we go left. What behavior is happening, in i.e. what's happening to our y values? So as we go left, are we going up or down? As we go right, are we going up or down? That's all we're trying to describe. But we can't use left, right, up, down. We have to use terms like x and y. So we'll use x's to describe left and right, and we'll use our y values to say whether it's going up or down. So if we look at this graph, as x goes to infinity, so that means we're getting really, really big. What direction are we going? We're going, if it gets really, really big, my x values are getting really big, we are going what direction? To the right. So realistically, we're just saying, hey, what happens when I go right? We go down. But what does it mean? What do our y values do if our graph is going down? They're getting really, really small. Down means my y values are approaching negative infinity. So as we go right, my graph goes down. But in order for it to go down, my y values must approach negative infinity. So as I go right, I go down. That means as x values get really big, my y values get really small. Now my next one says, what happens when my x values get really, really small in the negative direction? Well, big in the negative direction, but really, really small. What happens when they become negative? We go up. So this is saying what happens when you go left? You go up. So your y values get really big. So once again, I am basically saying what happens when I go really far left? I go up. Well, to tell me to go left, you make your x values negative. And tell yourself to go up, your y values go positive infinity. Questions? That's the big thing on end behavior. Let's do a couple problems with that. In fact, how about we take a second and you give them a shot? Give those next three a shot. Remember, I'm not asking you what happens between the lines. I don't care that this is absolute value. I just care what happens when I go left, what happens when I go right. So give it a shot. If you're writing in pen, maybe just do it in your head. If you're writing in pencil, write it down. You can always erase it. I want something that says, if I go left, this happens. If I go right, this happens. That's all I need using the terminology we just set forth here. So you should have two equations that look just like this. I would probably flip them. I usually do the left one first.
So we just have to memorize these?
Memorize it. Just know what I'm asking you. You shouldn't have to memorize this. You should just know what it means to go left on a graph. What does it mean to go up on a graph? So everything you need is right above this. Give it a shot, write something down. At worst, you have to erase it. And if that's the worst thing that happens to you today, that's probably you're having a good day. I want you to commit to something. Don't stare at it. Let's make a try it. Do you know the quickest way to learn something is to do it wrong?
Really? That's how I learned it, right?
With facts. Jonathan spin.
Just like the quickest way to get the right answer on the internet is to give the wrong answer.
No, you get the writing. That's good.
There should have been enough time to do all three of them, because I'm just asking what happens when we go left, what happens when we go right.
Well, as it goes left, it goes.
All right, I'm going to ask you in plain English. As this graph goes left, what direction do we go? As we go to the right, this graph goes. So now let's put that in mathematical terms. mathematical terms, we use x values to go left and right. So we should have something that says as x approaches negative infinity. That is what happens when I go left. You guys said it goes up, right? So as x approaches infinity, f of x approaches positive infinity. That tells you it goes up. So as x approaches negative infinity, that goes left. We go up by making it positive. All right, then we said as we go right. How do I go right on my graph using x values? Infinity. A positive infinity says go right. You also said it goes up. So we'd have f of x goes to infinity. Infinity goes up, negative infinity goes down. For x values, negative infinity goes left, infinity goes right. So once again, is this something we should memorize? No, you should just know what it means. The more you try to just memorize stuff, when I see this, write this, the less chance you have of knowing it for the quiz. If you know what I'm asking, left, right, up, down, it makes it a lot easier just knowing how to use those directions on a graph. So my next one, let's start out the same way. If I go left, what direction do I go? Negative infinity. What happens when I go right? I go down, which is negative infinity as well. So we just have to put that in math terms. To go left, we go as x approaches negative infinity. You said we go down. So in math, going down means our y values go to negative infinity. As x approaches positive infinity, as we go right, we also go down, so we'll go to negative infinity for my y values. All right, our next one. As x approaches negative infinity, what happens if we go really far left? We are going down. So I don't care what's happening in the middle. I'm just asking you what happens as we go left really far. As I go left really far, we go down. So that means your y values go to negative infinity. What happens as my x values get really, really big? We go up, which means we go positive infinity for our y values. F of x goes to infinity. So my advice is, if you ever get confused with these, just do normal English directions and try to make them mathematical. As I go left, what happens? As I go right, what happens? In fact, if you don't know how to write it mathematically, at least on the test go, well, as it goes left, it goes up. As it goes right, we go down. You're giving me most of the information. We're just going to lose some points because it's not really a mathematical way to tell me, but at least you know what we're looking for. Questions on end behavior going to infinity or negative infinity? Okay, there are times where as you get really big or really small, you don't approach infinity. Instead, you approach a specific number. So that's the last thing we're going to talk about. As x moves towards positive infinity or negative infinity, it is possible for your y value just to approach a number and not infinity. Yeah?
Would that number be the horizontal asymptote?
It will be the horizontal asymptote. That will be our number. So let's kind of do this in English the way we did and see why we can't answer it the same way we did over there. As I go right, does this keep going down forever? No, it approaches this number. As I go left, it approaches this horizontal asymptote. So we're not forever going up or forever going down in this scenario. We're getting close to a number. So we have to tell the person reading this what number that is. So as I go right, my graph approaches this horizontal asymptote where my y value equals a -1. So that means my f of x approaches -1. Now, when we get to harder stuff, we have to know which direction we're approaching, but for just now, we're just approaching -1. Don't go as approaching from the top or bottom. That'll be future stuff, but right now we're just approaching -1. What happens when I go really far left? I am also approaching -1. Okay, let's try this example here. Now, we're going to say as x approaches -infinity. So as I go left, I'm on the wrong one. As I go left, you see how this just gets close to that line? It doesn't go past. That would be my y value equals 0. So as x approaches negative infinity, our f of x would approach 0. We can picture this dashed line that I'm going to draw here, that this graph gets really close to it as we go to our infinities. Then we'll have as x approaches infinity, what does our y values do as we go really far right?
0.
It goes to 0 as well.
So is right.
Hey, real quick, let's go over these real quick answers. It looks like everyone had it, but I would say something like, as x approaches negative infinity, our y value would get very close to negative 3. As x approaches infinity, or as we go right, our y value also approaches negative 3. Now, when we get to the next one, it's a slightly different story. We have as x approaches negative infinity. So as we go left, we'll notice our y values skyrocket. That is where our y values go. Shh, guys. We have f of x goes to infinity. However, as we go right, it doesn't go down forever. It approaches this horizontal asymptote at 1, 2, 3, 4, 5, at negative 5. So our y values will approach negative 5.